This is just a quick reminder. We won't be able to fit everyone in this room. There's a fire marshal code that says, I think 500 is the max capacity. That doesn't mean you're not going to be able to see the lecture because we have basically video that will show up today on the class website. So if you can't find a seat, please, I have to ask you to leave the auditorium so the fire department doesn't come. But you won't get, there are no participation points for being in the lecture, like previous terms or whatever. So you don't have to be in the lecture. I wish we had an auditorium of 800 or 1,000, but we don't. So if you can find a seat, please do. If not, try to watch it over webcast sometime later today. Thanks. Okay, we're going to get started. Welcome to EE16A for spring semester. We're very excited to have such a high number of students. Can I get a little poll, just, see who's what year and things like that? So freshmen? Okay, good. I guess sophomores? Ooh, okay. Juniors? Okay. Seniors? Okay, we have a few of you too. Okay, great. Okay, this class is run by primarily by head TAs. Okay, so I would like to introduce Harrison. I guess Olivia is not around. Okay, so Harrison and there's Olivia too. So. If you have any trouble in class, for these listed topics, so questions not for Piazza, conflicts, emergencies, please send an email to head TA, not Harrison's email, like head TA at EE, and we'll try to deal with it. I'd like to introduce TAs now, because they're really the engine of this class. And you'll be seeing them quite a bit, both in the labs as well as in office hours, homework parties, and things like that. So maybe, let me just, okay. You can just stand up and kind of say hello. Let me see if I can give you this microphones. You have to do it like that.
Hi, I'm Alex. I'm a discussion TA.
Hi, I'm CJ. I will be the head lab TA, and I'll also have a lab section 11 to 2 on Wednesday, and then I'll have a lab office hour right after from 2 to 3. I guess a little bit of course history. I've been with the course for 5 semesters. I'm a senior, so this is the last hurrah for me. So I'm going to try to do what I can to make the labs awesome this semester.
Okay.
Hi, I'm Samin. I'll be teaching discussions Wednesday 11 to 12 and 12 to 1. Looking forward to seeing you guys.
Hi, I'm JMO. I'm a lab TA. I'll be teaching the lab right after this one and the Wednesday 8 a.m. lab.
Hi, I'm Angela. I will be teaching the Tuesday 2 to 5 lab and the Wednesday 5 to 8. So I'll see you guys today. Yeah.
Hi, I'm Ashley. I'm a discussion TA and the Gorilla Section TA. I'm going to be TAing Wednesday 5 to 6 and Thursday 8:30 to 9:30.
Hello, my name is Mudit. I'm a homework TA, so I hope you guys really enjoy the weekly homework.
Hi, my name's Harrison. I'm a lab TA. I teach Thursdays 11 to 2, and I also do homework party, which is 5 to 8 on Fridays.
Hi everyone, I'm Rachel. I'm TAing a lab discussion, and that will be on Wednesdays from 12, also from 3 to 4 and 4 to 5.
Hey everyone, I'm Arda. I have discussions Tuesday and Thursday, 2 to 3, and then I also do managing homeworks.
Last but not the least.
Hi, I'm Harrison. Vladimir introduced me. I teach discussion Tuesday, Thursday, 1 to 2, and I answer a lot of questions on Piazza and your emails, so get excited.
Okay, so one of the things to mention is that a lot of the TAs are actually former 16A students as of just like a few semesters ago. So, we have a very nice kind of promotion path. So we're looking always for people who really ace this course to kind of draw you in and basically have you help us make this course even better. So I'd like to introduce my colleague, Babak Azifar, who's going to teach this class with me. Babak, do you want to say a few things?
I'll say when I go up.
Okay, so Babak will tell his life story when he comes up. My name is Vladimir Stojanovic, and I'm teaching this class for the second semester, first time in the fall. A little bit about me, I graduated from Stanford, and then... But in my defense, I was probably the only grad student at Stanford who collaborated with Berkeley during his PhD. Okay, so gotta give me a little credit. Then I taught at MIT for a number of years, and then I decided Berkeley is really the best place to be at. And since then, I've never regretted it. Berkeley is really the best place to be at. So you've made the right choice deciding to come to Berkeley. Yeah. So I'm really excited about the quality of students and their maturity, actually. And you'll see that also from the TAs who are running this class. This is the only place where undergrads can run a class of this size that well. And so kudos to everyone on that. My research is about building systems out of integrated circuits. So I'm using kind of all of the techniques that we're going to be doing in this class, both the circuits and understanding of the underlying device technology, but also understanding of math and modeling so that I can basically build functional systems. And I'll tell you a little bit about some of these systems actually today, so you can get a flavor. But it's really connecting kind of the electron to software, essentially, in some kind of an application. I really also want to acknowledge Elad Alon, Anand Sahai, and a bunch of other professors who have put a lot of effort in setting up the framework for this class. And you'll see throughout this class a lot of the changes from other classes in the way the class is pedagogically set up, the topics, the modules, how we interact with you, how you approach learning. And so it's a lot owing to this crew over here. I think one of the fundamental things that they've set up, and you'll see kind of as we teach, is that we want to do everything in terms of design problems. Things that are not just analysis, like I give you a problem and then you go and analyze it and solve it, are really what awaits for you in life. In life, you will get a spec, or you will not even get a spec, you will get an intention. So you will come in and say, I want to build something, right? But that something has a function. I then need to define the specification for that function, and then I need to break it apart in smaller pieces and figure out how to implement each of the pieces, maybe from things I know, but maybe not, right? And so that kind of a design or synthesis technique is something we're going to try to teach you in this class. And that is a mastery that takes years to do. So if we start in 16A and hopefully follow through in all the classes till you exit Berkeley, you'll be very skilled to do these things. And you'll be kind of in a unique advantage with respect to everyone else out there who's still kind of just analyzing problems and not being capable to synthesize the actual problem. And keep this in mind whenever we give you a design problem and you start sweating how to do it. Just know this is for a greater good, okay? I already mentioned an army of, so the promotion path, but you'll see in the lab and also through your graded homework and these kinds of interactions, lab assistants and then readers and tutors are also the backbone of this course. So that's actually the first step into the course if you're interested to help with it. You ace the class, you're really excited about it, contact us at the end of the term. We'll definitely have reader, tutor, and lab assistant spots for you. Okay. The last thing about logistics is that there are two very important websites for you to keep in mind. One is, of course, the course website, and another one is the Piazza forum. I'm not going to go into the course logistics in terms of the policies and everything. That's on the course website, so please read it as soon as you, after this lecture. There will be a part of the homework on that, just so you can get familiar with how things operate and you're able to kind of follow the deadlines and things like that. Anything that you can't understand or you have a question, please post on Piazza. We're pretty good at responding rapidly to this, and so others can see. I know there's been a Slack channel that someone's trying to set up. That's also cool, but we're going to be using Piazza primarily for communication, just so you have it all in one place and to do it there. Okay. I really like to dive kind of into the technical content here. And I mentioned earlier that I'm personally interested in building things that I use integrated circuits, but go all the way up to some sort of an application. And we're listing here a bunch of applications that are really miracles of technology if you think about them. You take them for granted, but if you think at all the layers from the underlying device to circuits, to systems, to software, firmware, and then higher level application software, all of these things have the full stack, right? So these are really miracles of technology. If you look at Google Car, on top, there's this thing that rotates, and it's called a LiDAR. Basically, it's a laser beam shooting around, reflecting from surfaces or people, and then coming back to give you 3D information. So that's called point cloud. Well, for example, I build chips that can do that. You can beam light, beamform it from a single chip. You don't need these rotating mirrors and things like that. But you need to understand everything from how to manipulate light to the software mathematical models that will make use of that information to be able to, for example, hook up to the automated driving application, things like that. We'll later look at kind of what is actually happening in the iPad or these similar pieces of hardware. There's lots of technologies that have to come together to be able to do some things like that. Again, in drones, there's hardware that makes it fly. There's algorithms that make it fly. And in 16AB, you will be starting to form the basis for understanding how these algorithms work. What are the mathematical techniques to implement the control of a drone, right? Here is roughly the anatomy of the class. We're going to try to catch you up on some of the linear algebra basics. For those of you who haven't had that in high school, there's going to be kind of an intro into that, but always driven with some practical applications. So we're starting with things like Google PageRank immediately. Right? How does that work? This is one of the magic algorithms. Balak will tell you how much it was worth, or it is worth. But it's really astonishing that you will be able, in a month's worth of math in 16A, understand how that works and why it was so effective. Right? We will have a lab in parallel that will be a single pixel imager lab, and we'll talk about it more a little bit today, Again, you will use some basic mathematical formulations like vectors and matrices and such manipulations to be able to implement a sensor. The systems that I showed you in the previous slide are all about three things. You need to sense some information from the environment. You need to compute based on that information. And then you need to act. And that acting could be sending that information somewhere further, or could be actuating some motors, some things to feed back a response to the user or to another machine, right? And what we're trying to do here, both in the labs and math, kind of give you the basics of all the things. So the first lab will be about sensing. How do I sense information? How do I process it to display something? So imagers are a very good example of that. Then we're going to go into, again, the piece of sensing where you build hardware that basically senses what the user wants to do. And a good example of that are touchscreens. You have them everywhere around you. And every piece of hardware right now, from these tablets to your phones, touchscreens are everywhere. And so understanding how that works, what are the devices underneath, and how we can use it will be the second module. And of course, there are some circuits, some designs that we're going to draw from that. And then we're going to generalize, build some other types of systems based on these circuits. In the lab, we're going to be doing RN resistive and capacitive touchscreens. So you're going to have fun to play with those. But again, it's a whole chain from the sensor all the way to something happening on the computer that reacts to that sensing information. The third part, we're going to add some more advanced mathematical formulations that will help you build algorithms, for example, for locationing. Think about global positioning system. You have a receiver on every phone, in your car maybe as well. You will see how basic linear algebra techniques can be used to acquire the position from multiple beacons and things like that. And then the optimization techniques that go there to basically get even better results, eliminate noise and things like that with, for example, things like least squares, orthogonalization, things like that. So by this time, you'll have both basics in algebra, also insight into some more advanced algorithms, and some of the circuits and systems, how to build it. Right. I'm not going to go through these more detailed topics. They kind of sound maybe like gibberish to you right now, but believe me, you will be familiar with all of these things by the end of the term. Right. One important thing about 16A and why is it different than any other intro class that you're taking is that it actually gives you the base to attack EECS classes from both the, so to speak, bottom, which is kind of the technology level, as well as the algorithms, right? Which is kind of the modeling level. And so with some of the modules and labs that we're doing in 16A and B, you'll be able to go in ECS into the hardware and device-based sequence. Like 105 is the feeder class, and it's being redesigned right now to kind of accommodate the view in which we do 16A and B. But also, essentially going into modeling and algorithms. A lot of the algebraic techniques that we're teaching you here and in 16B are straight up used in machine learning, AI, and things like that. And you won't be able to understand these things unless you understand these basics. So this gives you the mathematical foundations to understand what's actually going on in fuel deep learning and any other machine learning algorithm. Okay. Computer vision, same deal. Okay, so let me see if okay. So let's start from the beginning, kind of the technology a little bit. Who can tell me what is this device on top? Telegraph, that's right. There are many inventors, but like, what's the most prominent name that comes to your mind when you think about telegraph? Speak up. Yeah. Morse. Yeah. So Samuel Morse is one of the latest telegraph inventors. There's been a bunch, even Gauss actually meddled with telegraph and things like that. But he was the one that basically figured out the alphabet. Morse code, and then also did some improvements in the US for the telegraph. And yeah, in 1937, it was a pretty polished device that people actually used for communication between cities, within the cities, etc. And then people got so confident using it for about 30 years that they just decided to lay the cable across the Atlantic. So that's this cable. And then decided to try it out. So what do you think? Did it work? No, it didn't work. Okay? A lot of effort. Can you imagine the journey? You're laying this cable, the ship is going, the investment in basically getting the cable all protected from salt water and things like that in 1866. Right? And it doesn't work. And people don't know why. They got so comfortable using the telegraph on land that they basically assume this is a God-given thing. It just works. You do a little pulse there, and it magically appears on the other side, and that's it. And why doesn't it work? Well, once they figured out there's actually forces of nature that work against you, they started modeling things. So they looked back into physics. At this time, physics was pretty established in terms of modeling electromagnetism, propagation, things like that. So yeah, they looked back at these models, and guess what? 10 years later, these models and understanding of the field advanced so much that they had this guy. Who can tell me who this is? Yeah. It's Alexander Bell speaking, basically transmitting words over these same lines. Right? But their understanding of what actually is happening when the electrical signal goes through the wire has actually greatly improved because they resorted back to physics and math to understand what's happening. So that's what we're going to be doing here as well. Whenever you try to build something, you first need to build a model of it so that you can predict what actually is going to happen. Even when you go to lab, you actually should always ask yourself, if I hook these things this way, what am I expecting to see? Resort back to the physics and math that you know, try to model it, and then correlate back to what comes back from the experiment. Same is with simulation. If you do some simulation in software, you should always know what the answer is, or what the answer should be roughly, to check what's happening. Right? You could have something shorted in your circuit, so you didn't wire it up correctly, and you'll be able to debug it because you know what it's supposed to happen. Right? You know because of the modeling that you do. So, using these basic approaches since then of mathematical and physical modeling and then prototyping and experimenting, people have been able, in sort of 150-ish years of working on the technology, to come to these devices. Right? These are super sophisticated devices. We're going to peel off one of them today just so you can see, but there's a lot of layers of technology here and hundreds of thousands, millions of people working on these things. One of the key contributors to having such sophisticated devices that you may not be aware of is essentially the scaling of these little switches that you have in your integrated circuits. These little switches are called transistors. They're like a light switch. They decide whether there is voltage or there's no voltage, whether it's current or no current, whether there is a signal or no signal. Right? And by combining them in different ways, you can realize logic operations. Once you have logic operations, you can have instructions for your computer to do something. Right? And looking at first very, very primitive machines, 4 and 8-bit processors, all the way up to processors that are right now in data centers, in servers, in your laptops, the scaling of these transistors has helped us go from a few thousand to a few billion. In just a matter of like half a century. Right? That is unprecedented. And most of this was just scaling. Right? There was innovation in chemistry and things like that. People used about 5 elements from the periodic table here. They use more than half of the periodic table right up there. They're actually exhausting right now the ways in which you can build it. But it has helped us fuel this enormous capability. Right? Think about this. Right? Here's Mark Bohr. He's one of the Intel fellows. He's 166 meters tall. And as you go down this scale, you see that today's transistors are actually smaller than viruses. Right. That, to me, is pretty amazing. I don't know about you. But we're very quickly hitting the point where we're right now at 7 to 10 nanometers. That's what Intel is looking at. Right? So yeah, we're like 10 times smaller than viruses. And it's at the point where you really are counting the atoms by hand to form this device. And you're not talking about some statistical effects and things. You're talking about certain atom being in the exact right place for this to happen. Right? So we're kind of on the edges of this approach. Right? Who can guess where the transistor is on this picture? It's a little I Spy kind of thing. Anyone? Yeah? You mean where the red dot is? Okay, so you're thinking maybe it's here. Or here. Here? Okay, well, it's actually right here. Little tiny thing you can't even see is a transistor. And all of these things are actually metal wires that are trying to connect these transistors together. Right? In fact, these metal wires are the biggest culprit in these integrated circuits. Reason why I'm mentioning this to you is you're now just starting, right? And people who started 20 years ago already encountered pretty mature technology and were able to ride that technology wave. You should be thinking about basic principles of design, physics, and math that you will integrate here and then use them 20 years from now to operate who knows what technology. Just remember, people who were in school in 1990, okay, they had access to this type of technology here. And then now they're mature designers and working with today's technology. So they had to incorporate these basic principles in design techniques that will carry them through that very sharp slope. Same with you. Who knows what you're going to be working with molecular biosystems, some very, very funky technology, 6 orders of magnitude more capable than what you have today in your pocket, right? But you have to understand the math and physics enough to basically be able to harness that power. Right? So always think about it that way. That's essentially how these guys thought about what they were doing. Who can tell me who this guy is on the left? Yeah, that's Claude Shannon. He's actually a very interesting character who started off at MIT for his master's thesis. He looked at mechanical relays. These are mechanical switches, not transistors. And he was trying to figure out how to put logic functions based on them. But then later on, he was much more interested into how to communicate a piece of information from one point in space to another. Previously, before him, just like the Atlantic cable, people had no idea how many bits of information they can send from one point to another and what limits these things. They thought, okay, it's noise, but and there was just empirical formulas. Nobody had an idea what's the upper limit. So he sat down and derived basically the notion of capacity, which is the upper bound for how much information you can send on any communication channel. Right? And that, when he did it, people thought, oh man, that's like a ceiling. Nobody will ever be able to achieve that. Well, guess what? Today's radios that you have in your pocket operate at like half a bit away from the capacity of your communication channel. And that's all owing to the techniques you're going to be learning in 16A and B. Essential algebra, communication techniques, how to process the signals so you can achieve that level. Of course, the underlying transistor technology has helped with that too. But again, we're very close to the limit that he set up for us. Alan Turing, who's on the right, has also set up the basic foundations of the computer architecture for the processors and digital technology that we use today. Right? And so will be in 16AB, and then if you go through 61C, you'll be seeing a lot of components and systems that he set up. He set up the notion of a program with instructions, and then a part of the computer that executes these instructions on data that's stored in memory. These things were previously not really connected or organized that way before he looked at it. Okay, so again, a lot of these basic techniques that these guys set up are embedded in all of these devices. So we're going to touch on them throughout this course. What we're aspiring to in 16AB, and hopefully later, is to make you basically a Jedi of these techniques. I'm not kidding, because I told you what you're learning today, 20 years from now, you'll still need to operate things that have 6 orders of magnitude more power than what we see today as technology. Right? That's how these guys 20 years ago, who were also sitting in Berkeley and taking classes, that's what they do now. Right? They operate stuff that's 6 orders of magnitude more powerful than when they were in school. There were basically tape feeders and floppy disks, nobody remembers, right? But now, you're looking at much more sophisticated technology that's going to get even more sophisticated. Right? So let's take a little bit of a look at what's inside an example device that represents kind of a reasonable state of the art. Okay. Well, first thing that you saw on the previous slide was the big screen, right? So that's the touch screen. You will actually be doing a very similar thing in the lab and building it from scratch yourself. And we're going to cover that in class. Apart from the touch screen, there are basically a number of components here. The battery uses very sophisticated chemistry. Physical world interaction is through speakers, right, that modulate the air. And we're going to touch a little bit on this in the course. How do you build something that turns a bit of information into a sound wave? Right? What's in between? What type of circuitry can I use to achieve that function? Right? And then other user interfaces, like a home button or the touchscreen, we're going to be building things like that in the lab. If you look at the brains, it's just this tiny little board over here. And on the board, basically a tiny little integrated circuit with billions of transistors. Then you look into that circuit, see a lot of operations that are happening. Among others, let's say there is a dedicated block to process images and videos. Right? And that block will use a lot of the techniques that we use in this class, algebraic manipulations on the image vectors and things like that. There is a camera, which is another miracle of technology. If you think about how it is built in the integrated circuits, micro-lensed, things like that, it's a beautiful thing. We're talking about, like let's say 12 million pixels times 3 for different colors. So that's actually quite a bit of devices packed on this little chip. So we're going to, in this first lab, actually see what are the basics of how these things work. Right? Does anyone know, based on what effect do we get to sense the light, or basically turn a photon of light into an electron that we can collect in this integrated circuit? Yeah? Yes. So is that a significant thing? Anyone? Yes? Yes, it is photoelectric effect. What award somebody got for that? Yes? What award? Yeah, so it's just a Nobel Prize, basically, and it was given to Albert Einstein, right? They didn't give it to him for theory of relativity because they actually couldn't confirm it. Now we know actually we're sensing gravitational waves and we know actually these things are real. But they gave it to him for this. It was still a significant effect. You have a lot of cameras on you, and so it's a very useful thing. But just keep in mind that he was using these very sophisticated mathematical models, like for the theory of relativity, to predict something that nobody could detect 100 years ahead of time, right? Okay. I mentioned that behind the camera, there is a chip that basically has circuits on it that does digital computation that will do a whole bunch of these blocks, and you'll be doing them kind of in Python, kind of in your lab. But nowadays we have the power to take very complex mathematical operations like color transforms, compression, things like that, that will compress the information from the image to something that the human eye can see just as well with much less information. We will be using algebraic techniques to do that. Apart from just shooting funny pictures, and having fun with your friends or landscapes, people have always been interested in using imaging to help, a human condition. So early on, they had no choice but to open up the person and see what's inside. Right? But soon they realized this is not a very repeatable technique. Can't do it very often. So yeah, they try to figure out a way how to use some other way of sensing what's happening inside a human being. And now we take all of these techniques for granted. There's a variety of them. There is X-ray, CT scans, MRI or functional MRI, even ultrasound. These use electromagnetic waves. Ultrasound uses kind of sound waves. But the notion is the same. I'm sending some interrogation signal. It's an electromagnetic wave of some frequency. And I'm detecting what scatters back, or what gets reflected back, or what gets transmitted through a certain medium. And by understanding that intensity, I can actually figure out the depth or the type of that material. And Babak will talk a lot more about what are the mathematical techniques through which you actually disentangle the information. Because the information, as the light X-ray passes through the body, encounters many tissues, right? How do you disentangle the exact tissue that you care about? Obviously, you have to do several measurements to be able to do that. And we'll go exactly into why that needs to happen. Right. But you'll be learning these techniques right off the bat as we're starting, in fact, today in the lecture. Right. Again, this is kind of what I mentioned. We're going to shine some excitation, go through the subject or reflect back of the subject, and then detect the energy. So what's the simplest imaging system that you can think of? I just showed you we need a source, we need a subject, and what else do we need? Yes? Sure, mirrors, but let's assume I can basically record what goes through the subject, right? Or what gets reflected off of the subject. But I need to detect, right? So I need a detector. So let's say I have my, okay, let's see, this is going to work. Let's say I have my source. So it's essentially diffuse light, right? So it just goes, parallel lines of light go and hit a subject, right? And some of the light will basically get through and will be attenuated. As it gets through the subject, depending through which tissue it went, it will be attenuated by a certain amount. Right? And I will use one detector on this side. So this is a detector. And then what I'm going to do is I'm going to move this detector in location vertically and do consecutive measurements. So this is, so to speak, my axis, right? So X. And I'm going to slide this detector through every point, and I'll label this point 1, 2, 3, etc., to n. And then I can plot something that looks like this. So this is x, bin 1 through n. And then I'll plot, so here I get all the light because the light just goes here straight. So I get, this is the intensity of light. So I'll get the highest value. And then as I'm going into the subject, I'm going to be getting smaller and smaller values. So I'll be able to get some sort of measurements like this, right? This is the same as if I took a one shot and I had n sensors, right? N detectors. It's just I'm doing it a little bit more slowly. And this is exactly what you're actually going to be doing in the lab. We're going to have a source, and then we're going to have a detector. Now, we're going to do a little twist in the lab because we don't want you to move things around. It's kind of cumbersome. So who can tell me what's the other way to do this? In this case, I used just light, and then I was moving my source. What's the other way to do it? Yes? OK, so the idea is to move the source, but there's something special now about the source. I had a very tiny detector there that was just looking at what's happening in a particular pixel of space, right? And the source was this giant piece of light. So if we're going to do a dual thing, what do I need? Yes? OK, you're saying LED because it's small? OK, so you need a focused beam of light, right, that just shines on one piece of the object. And then the detector is a very big detector that collects all the light that reflects from that tiny piece of the object. So what we're going to have is, again, the object. We're going to have something that moves this source of light. And then we're going to have a big detector. So for every beam of light that we shoot, we're going to shoot it in a different location, right? And then as it goes through, it will scatter. But this detector will pick up all of that and say, OK, that was from illuminating basically this piece. So again, we're going to have something that as we move this from 1 to n, we get the intensity to go something like that. Okay? And that's actually exactly the setup that we're going to use in the lab. We're going to use a photovoltaic cell and a little circuit that collects electrons that get turned in from photons, because this turns photons into electrons. Don't worry about this. You'll know all about it just in a few weeks. And then we're going to use a little Arduino board to collect this information or turn it from analog to digital domain so that your computer can interpret this and graph it and plot it, things like that. Right? And actually, this is a cute setup you're going to use. Our pointy source is going to be the projector. So we're going to make the projector shoot a pixel at a time of light on the image. And then off of that image, we're going to reflect the light onto the PV cell that's going to collect all that light. And every pixel that the light moves will be a new measurement. And in n pixels, you'll scan the whole image and get that information. And then you'll see some mathematical techniques how we can speed this up. That's where this equation solving comes to place. OK, so this is the imager with just one sensor. It's kind of illustrative to do it. It's kind of an easier math for you to understand and set up in the lab. Of course, modern cameras take 12 million of those in one shot. But they still require math to post-process and deblur and compress and all these things like that. In a more complex scenario, as I said, you're going to want to localize the information from within the image or volume and know what's happening exactly there. And that's what Babak is going to talk about. You're going to need even more sophisticated math and more measurements to be able to de-embed that information. Okay. So with that, I'd like to introduce Babak now, and he'll start basically discussing with this intro to tomography. And I'll see you in a few weeks. One other thing I wanted to mention is both of us have office hours. Please come not only to talk about homework, I'll be in homework parties too, but let's just talk about conceptual stuff that we do in lectures. Because if you understand the conceptual stuff, problems are going to be easy. Okay. But if you're shaky on conceptual stuff, that's going to be a long-standing problem. So I look forward to seeing you in the office hours. You need both. Oh, yeah. You need both. Just put them on this. What was that?
Morning, folks. This is the earliest I've ever taught. I'm a night owl, so it's going to be an interesting semester. Yeah. So let me first tell you a little bit about how I like certain things done. This is my name, and I'd like you to call me by my first name. I know that depending on the culture you come from, that may be awkward at first, but hopefully we'll try to get you used to calling me by my first name. We try to make this course as fun for you as possible and as educational for you as possible. We're still in the learning curve, even though we've done a pilot and we've done 2 or 3 semesters of the full-scale version of the class. It's still in flux. So I want to encourage you to tell us about the ways you think we can improve the course as we go along. It won't help you any if you wait till the end of the semester for course evaluations to do that. We're very open to feedback. The TAs will collect that kind of feedback from Piazza for those of you who are outgoing enough and bold enough to make those comments on Piazza. But in private also, I welcome any comment or any meeting with you to discuss things. Now, I'm going to take a little bit of time setting up my chalks. I'm back to the chalkboard after several years. This is actually my home turf. So in the meantime, I want to tell you about a way I run the class, the lectures. My lectures are very interactive. I ask questions. I ask you to talk to your neighbors. And then we'll go around picking people to answer questions. Now, some people feel awkward about being picked to answer a question. I want to give you an assurance, first of all, that you are never going to be cold called. There is always a period of time that you get to talk to your neighbors to discuss things. I'm going to start soft and see how that works. If it works, then I'll stick with the new method. So that in the old days, or up until last semester, I would pose a question on the board, I would ask people to talk to their neighbors, and then somebody would pick the first person, and that person would be responsible for answering. Then the next problem, that person would pick the next person, and so on. So what I'm going to try this semester is when somebody is selected, the people in that group will decide who is going to do the talking. Okay, so if you get selected, you're not necessarily the one who has to answer. This is not an attempt to embarrass you in front of the class. This is just a motivation to keep you engaged and not sitting there passively trying to absorb information, which is never effective. So what I'd like you to do now while I set up my chalks is to talk to your neighbors. So the groups I want to have are ideally size 3 to 5. So you guys, each row here would be one group, and then when you get up to the back of the class, obviously you have to split into two groups. And here, I guess 3 or 4, whichever is comfortable. So please introduce yourselves to each other. Exchange all kinds of fun information. I think you need one more. Okay, thank you. This is where I do time. But please bear in mind that with 800 of you, if I were to open the door every time somebody knocks, I won't be able to get any work done, including prep for this class. So if you ever want to meet with me, if it's about some technical issue, logistical issue about the course, your best bet, first stop should be your peers. After that, the TAs, lab assistants. But if there's something that's serious enough that you want to talk to Vladimir and I about, then please send an email with your availability in the subsequent several days, and we'll pick a time slot that works for us, and would be happy to see you in our offices, at least in my case. Okay? So I've had friends who've flown in from out of town, and they've knocked on the door without telling me that they're coming, and they went disappointed. So it's just a way of keeping my sanity. All right. So the topic. Any questions about anything I've said? Yeah. If you're struggling with the class, if you want to talk to me about possible research, finding undergraduate research with somebody in the department, people talk to me about pretty much everything under the sun. I should mention, by the way, that the earlier you tell us if you're having problems, whether specifically with this class or family issues, financial issues, whatever it is, it's detracting from your performance in this class and in the school in general. The earlier you tell us, the more options we have available to help you. If you come to me on the 12th week of the semester and say, I've been having this trouble, I've been working 3 jobs, I haven't been able to pay attention, I bombed the first 2 exams, there's not a whole lot we can do for you there. Okay? So you don't have to tell us details that you don't feel comfortable telling us, but the earlier we know that there's something wrong, the better. But I'm happy to chat about pretty much anything under the sun. Now, before I start the topic, Vladimir reminded me, there's this thing I used to do in the old days, and I only started redoing it at the end of the last semester. So there was a professor at Georgia Tech whom I didn't know personally. He's passed away now. And a publisher's representative told me about this, that when he went to visit him, as he was approaching his classroom, he saw people standing up and raising their hands saying, "Banzai! Banzai! Banzai!" What the heck was going on? So he asked the guy, this professor, and he said, that's a way of me giving students a break. So if you see me ramble on for too long, please yell "Banzai," and if it's at a reasonable juncture, I will pause and give you a break. There's actually research, that's been done about concept retention and time. Some measure of concept retention. It works like this. And this is at the 10-minute mark. Okay? So what I try to do usually when I pose a problem and I ask you to talk to each other, I typically give you more time than you need. So you kind of decompress. And that's my way of basically resetting your clock every about 10 to 15 minutes or so. Okay? It also tends to give this large class a feeling of a small classroom. Okay, let's get started. The first topic in this class, well, 2 modules in this class are about linear algebra. And we'll also try to tie that linear algebra with the second module that Vladimir is going to start in a few weeks, the circuits module. And I know that many of you have probably taken, how many of you have taken Math 54 or equivalent? Woo-hoo! Why are you here? This course technically does not require any linear algebra. We try to teach it from the ground up. And if you take 16A and B, I think the ultimate goal, has it been passed already? Yeah, so it's actually passed already or proof that if you take 16A and B, you don't have to take Math 54. So those of you who haven't taken Math 54, don't feel like you're at a disadvantage. The other guys, see, what's going to happen to those of you who haven't taken Math 54 is that your peers who have taken Math 54, they're just going to say, oh, I'm cruising. They're going to cruise to the first exam. And they think that the rest of the class is also going to be like that. And then they're going to be hitting a brick wall by the second midterm when we test them on circuits. So I caution those of you who have taken Math 54 to not become passive. So, of course, the first topic are linear equations. And linear algebra is linear equations and Gaussian elimination. So that's what I'm going to get started with, Gaussian elimination. And the way I'm going to introduce this is by something that Vladimir talked about in his introduction, which is imaging, in particular tomography. And the way I'm going to do that is by talking about an experiment. How do you spell this guy's name? Bourguet, Lambert, Beer law. So this is an experiment that started in the early 18th century. What was it? 1729. And this guy was around 1760. And this guy was around in 1852. And essentially, this experiment involved shining a monochromatic beam of light onto a substrate of length, we're going to call the length A. This substrate, some substance, you can, in the case of medical imaging, it would be body tissue. It's homogeneous, so it has a uniform structure. The light, or the X-ray, whatever it is, that shines has a certain intensity coming in, and it has a certain intensity going out. So I in, I out are input and output intensities. A is the path length that light travels, and X is, I'm changing notation. Typically, people use, in the physics community, they use mu. But I'm going to use X because it's consistent with the formulation of linear equations that we're going to pose. This is the attenuation coefficient. So now, I don't care about units. So the light intensity you can think of as photons per second. Whatever the units are, the input and output intensities have the same units. A is the path length, so meters. And X is an attenuation coefficient. Again, it depends on the other physical parameters. But well, actually, what is the unit of X? If I give you the equation that these guys came up with, which is that the intensity at the output is the intensity at the input times e to the minus a times x. So that's the Bourguet-Lambert-Beer law. the output intensity is the input intensity times this exponential, where in the exponential you have the path length and you have the attenuation coefficient. So what is the unit of the attenuation coefficient? Tell your neighbor. Okay, it doesn't take that long. I'm going to take a volunteer. You are? What's your name? Bate? Bate. What's the unit? 1 over meters. So this is meters. Okay? Now notice the role of A and X are interchangeable. They're both in the exponent. If I double the path length, the output, and without changing anything else, if I double the path length, I get a certain output intensity. Now, if I go back and keep the original path length and double the attenuation coefficient, what's going to happen to the output? Does it matter whether I double the attenuation coefficient or double the path length? Think of this. So maybe I should, to make it clearer, the attenuation coefficient is related to density. If you want, you can even think of it as proportional to density. So imagine I have a container of water and I put in some drops of ink in it, let's say 10 drops of ink, and I shine the beam and I measure the output intensity and I compare the input and output intensities. And so the question I'm asking is, if I take the same density of ink and add volume so that this length is doubled, then I measure the output. Compare that output with the original container where instead of 10 drops, now I have 20 drops of ink. Would the output light intensity be different in the two cases? Why not? Because you're looking at the product. If I double this, the exponent is doubled. If I keep this the same and double that, the exponent is doubled. So there is this symmetry, algebraic symmetry between the A and the X. Now, I don't want to harp on that too much. Any questions on what I've said so far? There should be an obvious question, because I've said I'm talking about linear equations. Is this a linear equation? Who says yes? Who says no? Okay, well, we've got a problem. Is there a way to convert this into a linear equation? Well, tell each other. How would you convert this into a linear equation? Okay. Can I have a volunteer to explain to me how I can turn this into an equation linear in X? X's are unknown, by the way. The input intensity is known. The output intensity we measure, so that's known. The path length is known. So what we don't know is, what is the substance that I'm shining my light beam through? What is its attenuation coefficient? And just to give you a more global picture, the idea is the way it connects with CT, if you ever go for a CT scan, is that they shine a beam into your head and comes out the other end. It goes through a path that's not of uniform density. So if you think of various cells in the path of that light beam as having different densities, what you want to do is figure out what the densities are in each of the regions along the path of the light beam. And because the attenuation coefficient is related to the density, by figuring out what the attenuation coefficient is for each of those tiny segments, you can figure out the density. And so if there's a mass that doesn't belong there, if there's something that's too dense, like in a tumor, then you detect it and you figure out exactly where it is. Okay, so that's basically the idea. But we start with one cell. So how do I go from this equation to something that's linear in x? Volunteer? Yeah, you are? Neil. Go for it, Neil. Okay, divide by I in. So I have I out over I in equals e to the minus ax. And then log both sides. So I'm going to take this ax to the other side. So minus ax is equal to log I out over I in. And then divide by, if I want to absorb this negative into the log, can I do that? What would I write? ln of I in over I out. By the way, this here is called the transmittance for obvious reasons. The ratio of the output intensity over the input intensity. And I don't like carrying out all this junk here. So because I know what this is, I know what this is, I can take the log of that ratio. I'm just going to call this B. Okay, so B is known. So my equation now is AX equals B. And if you want to solve for X, well, you can do that, right? This is the scalar version of the equation that you're going to see so many times, and those of you who've taken Math 54 have already seen so many times that you might even get sick of it, which is the matrix vector equation. So this is the scalar version, okay? AX equals B, and one way to look at how to solve for B is, well, you invert A and multiply it by B. The matrix vector form is this, where we'll learn how to solve this equation, perhaps looking at it this way, although that's not numerically the way people do it, especially for large-scale matrices. Okay, so this is the scalar version, scalar, and this is the matrix vector version. And I'll talk about what vectors are and how we manipulate them later. Right now, don't worry about the matrix vector form. But the symbols are analogous, okay? This is basically the reason I didn't want to use mu, because A mu times B looks kind of awkward, and it'll throw off those of you who've taken Math 54. Okay, now, how are we doing so far? Everybody here? Cool. Now, what happens, let's extend this picture to the case where I shine my beam of light through a series of individual cells that have different attenuation coefficients or different densities. How would I figure out the relationship between the output intensity and the input intensity? You think you can work with your teams to come up with a scheme? I'll even help you. Think of the output intensity at the interface between x1 and x2 as I1. this one as I2, and this one as IN minus 1. Perhaps that'll help you get started. Okay, go for it. Show me what you've got. Actually, I'll leave this down for now. Oh, I forgot to tell you, each of these has its own length. Okay. Any ideas? Is there a volunteer in the house? Where? Speak up. I can't see your hand if you're raising. Go for it. What's your name? Swapnil. Go for it. Work with me backwards. I out is, so I out is what? Relative to IN minus 1. If the intensity going into
is IN minus 1.
Uh-huh.
Power negative
xn. Okay, and IN minus 1 related to the one before that is?
IN minus 2 to power negative AN minus 1 xn minus 1.
So this is that, and then we have that extra factor there. So if you were to write it all the way to the input, what would it be? Okay.
We already derived the formula for a single cell.
Right.
So if we consider, let's say, A1x1
Okay.
is equal to ln In by I1.
Okay.
A2x2 is equal to ln I1 by I2.
Okay.
And so on and so forth till An xn is equal to ln In minus 1 by I out. Adding all of them together, we get
You multiply the logs.
Yeah.
Okay, and you'll have numerator-denominator cancellation. It's essentially the same as what I've done here. So basically, if you follow cell by cell, you'll see that the input goes in, and these terms keep popping up at every stage, right? If I work backwards. So I'll have the product of all of these. And that's essentially, so I out is I in e to the minus. Can you tell me what you got?
A1x1
Uh-huh.
A2x2 blah 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 AN xn.
Yeah. And this is a scalar. If I divide both sides by in, take the log, what equation will I get?
A1x1
Uh-huh.
is equal to ln I by I.
Is equal to whatever, some b, right? So again, I have a linear equation in the unknowns x1 through xn. The path lengths are known. Okay? Any questions? This is just a series application of the single cell problem. Okay. Now let's do another example with a 2x2 cell. And I'm going to make it simple. Assume that the path lengths, the dimensions are all 1. So this dimension, it's 1. This dimension, it's 1. And so I have 4 unknowns. At the very least, I need how many equations to solve for the 4 unknowns? 4. So let's say I shine a beam in this direction, and I measure something at this end. And I'm going to call that measurement B1. So it would be the path length of this cell, which is 1. So A1 is 1. Plus the path length times x2. And I make a certain measurement. Let me actually write that here. What other measurement should I make? Huh? Wait. Go for it. Yeah. Go through x3 and x4 and call whatever that measurement is B2. So I have an equation involving x3 and x4, and that's my second measurement. What else? X down from x1 to x3, I'm going to call that B3. And so I have x1 plus x3 equals B3. What else? Well, there's only one left. Yeah. x2 and x4. I'm going to call this B4 prime. And that prime should flag you that something is going to So tell me, do I have what I need? Who says I have what? Tell your neighbor, if these 4 equations are going to lead to a unique solution for x1 through x4. Remember, we want a unique solution. If I'm looking at 1, 0, 0, 1 as opposed to 0, 1, 1, 0, if the left lung and the right kidney have tumors as opposed to the right lung and the left kidney, you don't want the surgeon to mix those up, huh? You want to know exactly where these are. So is this going to give me, are these equations going to tell me what the attenuation coefficients are? Talk to each other. B4 prime. Okay. Who says we can? Who says we can't? Oh. The rest of you, you're in the shady region, huh? Okay. Why can we not? The correct answer is that we cannot. Why is that? If I label these equations E1, E2, E3, and E4 prime, what's wrong with this system of equations? Yeah? Determinant. We're not there yet. That's a different lecture. Be grounded. Determinant. Oh, 4 by 4. You want to give it another shot? E1 plus E2 minus E3, if all the measurements are exact and perfect, will give us E4 prime. Another way to see this is if you add these two together, you get the same as adding these two together. So one equation, in particular that last measurement, has not given us an independent measurement. So it doesn't matter what the values are that we measure. The fact is, the very idea of measuring this last column dooms this measurement, dooms this system of equations. So let me just say here, E1 plus E2 is equal to E3 plus E4 prime, which means that E4 prime can be expressed as a linear combination of the other three equations. In other words, E4 prime is not giving us new information. So what would I do? What measurement would you suggest I do? Through x4. And if I call that B4, then I will get, so what's the path length now? What's your name? Kevin, what's the path length now? Root 2. So I have root 2 x1 plus root 2 x4 equals B4. And that's the same, you can, why don't we call it something else? B4 hat. And that means x1 plus x4 equals B4 hat over root 2. Let's call that B4. So that now gives us the fourth equation, and we can solve that. And I'll get to what is it about this system that doomed it at the beginning of the next lecture, where we talk about Gaussian elimination. We ran over time this time. OK, see you on Thursday.